talk about Z transforms, frequency response, and a whole range of things connected to discrete sample elements, particularly from an FIR space, and kind of look at how some of these things connect together. And one of the things you start to see is that you can start with an FIR filter function, y of n. There's a whole bunch of delayed and weighted values when you sum it together. Okay, that makes sense. You can take a Z transform of that directly, and then when you actually do the Z transform of that, you actually know you can directly connect to frequency response. And the sort of typical frequency response for an FIR filter would look like this. So you begin to start to realize that there's these interesting pairs between sort of the discrete time signal, the Z transform, and the frequency response. There's a whole conversation in a continuous space as well, but we're going to stay to this discrete case in this situation. And so what you'd find is here's my x of n, my x of z, and my x of omega. And what I'm going to find is that a couple things. One, all of them are linear. Yay, that's great, and that's the sort of definition for linearity. The second thing is that you definitely get this case that convolution in discrete time turns out to both be the product in the Z transform domain and the product in the frequency response domain. Again, not terribly surprising if you're familiar with other frequency response spaces, because you would imagine you're going to get product for, say, like a Fourier transform. The same thing happens, Laplace transform. And in fact, in many, many cases, the big thing that you're looking at is you're taking convolution and making it into a product. The other thing you also get is an interesting property here from discrete time to frequency response. If I end up modulating by a frequency, guess what happens? It looks like x, my frequency response just simply shifts in terms of its being at a different frequency now. So instead of just being omega hat, it's omega hat 0, and you're thinking, that's interesting, because it's exactly the opposite property of the delay property we had here. And this duality is actually very important because it tends to mean if I've got a transform going from discrete time to frequency response, it tends to also be the reverse also happens. If I were to substitute omega for change the omega for n and so forth, I end up getting a very similar behavior. This duality definitely shows up in the discrete case. For those who are familiar with the continuous case, you get the same thing between signal and, say, Fourier transform. This turns out to be very, very useful. One of the other real interesting sort of pieces is what's also typically known as Parsifal's theorem, which basically says energy is conserved in both cases. So if I take energy, which is this sort of the square root of the amplitude, if I take the square root of the amplitude of the input, it's equivalent to sort of taking the integral over all of the power in the Fourier domain of it. And so there's lots of different ways to go back and forth on this, but basically power is conserved. So the signal squared in any domain is preserved. And lots of different formulations of that show up. One other thing that's really interesting is that you can cascade systems. And so it means that if I were to take an input and I cascade it through two of these, well, that looks like a convolution of two of them. So basically a good way to approach it is it's just the convolution of these two blocks. Well, that turns out to give me a linear system. So it looks like I have just a single linear system as a result. So I can make a linear system out of 2 or 3 blocks, and it's really 1. And in fact, if I do it for 3, I see the same thing happen down here and the same structure. Oh, by the way, you still get that the product shows up for the Z transform or the frequency side of the domain in the 2 or 3 case. And in fact, in general, any cascade of linear systems results in a single linear system in any of these cases. So hopefully this gives kind of a rough sort of sense of some of the key pieces that cross over and that you can kind of use in these different places.